We're going to take a look at that two-step mechanism that was proposed in the last video a little bit more closely now. To refresh your memory, here's the two-step mechanism that was proposed. We have a bond breaking step followed by a bond formation step to give an overall substitution. If we were to plot an energy diagram of this reaction and so looked at the change in energy as the reaction progressed, it would look something like this. And hopefully you remember from general chemistry a couple of things here. This is a two-step process, right, which we kind of already knew. And so here we have step 1 and here we have step 2. And let's label a few things. At the top of each one of these hills, we have a transition state, which is symbolized by this notation. And this would be the first transition state. This would be the second transition state. We also have an activation energy from here to here for step 1, and then from here to here for step 2. And then finally, we have this energy gap here, which is the overall, usually this is delta H of the reaction. Technically, it could be delta G, but oftentimes the entropy change is insignificant, so these are plotted as functions of enthalpy changes. And then if you recall, here in the middle, in this well in between the two, this is a reaction intermediate. Let's look back at the two-step mechanism that was proposed. You'll see that the first step of the mechanism is what we call the slow step, or you might have heard the term rate determining step in general chemistry. And we're going to look back at the energy diagram for this reaction, but you would predict based on the energy diagram that the first step is the slow step. The second step is the fast step of the reaction. Also note that the intermediate that's formed that we pointed out on the energy diagram is this carbocation. A reaction intermediate is something that is produced in one step and then used in a later step in the reaction mechanism, so it doesn't appear in the overall reaction. Since the first step of the reaction is the slow step, or the rate determining step, that means that the rate of this reaction is dependent upon the rate of that step. And so if we were to write the rate law for this reaction, it would appear as follows. It only depends on the concentration of the reactants, which happen to be just the alkyl halide here. And don't forget that this lowercase k is a rate constant that is unique for each reaction. What's not shown here is an exponent of just 1, because if you recall, the slow step of the reaction only depends upon one molecule of Rx coming apart, essentially. This is a decomposition reaction. And so there's only one molecule of this in the rate law. And when a rate has an exponent of 1, like this, we say that it exhibits unimolecular kinetics. And so overall, we would say that this is a nucleophilic substitution reaction and that it's unimolecular in nature. So the abbreviation for this is going to be S subscript N1, or the SN1 reaction. Let's look back at this energy profile and fill in a couple of things. So now we know that the intermediate here is a carbocation. We also discussed that this is the slow step. Step 1 is the slow step of the reaction, and we see that because the activation energy barrier, which is here, E sub A1, is much larger than E sub A2, and recall that higher activation energy means slower rate. And so it's not surprising that step 1 of the reaction is the slow step of the reaction. And again, at the top of the hills here, we have transition state 1 and transition state 2. Let's talk a little bit more about the slow step of the reaction, and in particular, the transition state of the slow step of the reaction. So the activation energy barrier that is causing this step to be slower is directly related to the stability or instability of the transition state. And a more stable transition state leads to a lower activation energy barrier, which leads to a faster reaction. So it'd be nice to know what that transition state looked like, because any factor that would help to stabilize that transition state would lower the activation energy for that step and then speed up the reaction. Recall that the slow step of the reaction looks like this, where the alkyl halide is coming apart, so to speak, and you're getting a cation and an anion forming during the process. The transition state is basically taking a snapshot of that bond breaking. So something like this, where the sigma bond is coming apart, and the X is starting to become negatively charged, and the R group, or the carbon, is starting to become positively charged. So the question now becomes, does that transition state more closely look like the starting material or the product? In other words, is the carbon atom closer to a neutral charge or closer to this +1 charge of the carbocation? You can read about something called Hammond's postulate in the text, but the premise of this, the basic idea, is that whichever species is closer, the transition state is closer in energy to, is the one that it's going to resemble more closely. So if we take a look at the two energy gaps here in pink between the starting material and the transition state, versus here in green between the intermediate and the transition state, we see that the transition state is closer in energy to this carbocation. What this tells us is that the transition state here starts to look a lot like the carbocation. So at the top of the energy hill there, so to speak, you're getting a lot of positive charge buildup on that carbon. Therefore, anything that we do that will stabilize this carbocation will lower the activation energy of the step. So we're going to be interested in how to stabilize a carbocation, because this is going to lead to a lower activation energy of the slow step of the reaction. In the next video, you're going to take a look at factors that help to stabilize this carbocation.